chat with Professor John Willis. So please take this opportunity.
You see,
Andrea has a question.
Yes.
Yes. Thank you, Professor Willis. This was a beautiful talk. This is Andrea. I wanted to ask just one question about, I think when you were showing the different dispersions for the constitutive parameters, and my understanding is that you are justifying the anomalous dispersion of one of them by saying that the total energy in the system, when you consider both the plane wave propagation, is still positive, even if one of the elements gives a negative energy, let's say, like a kind of.
That's right. Yeah. Yes.
So my point that I think we were having that discussion long ago. I think you mentioned that.
Yes.
is that my argument is that this way of homogenizing is prone to problems. In fact, I think you were showing later in one of your examples that by using a simpler model, you would get a transmission coefficient larger than 1 in some region of frequency. The issue for a finite slab, the issue is that if we believe that our homogenization model applies independent of the form of excitation, then we cannot accept that any of the constitutive parameters violates the passivity conditions, not just the combination of them for a specific excitation that is a plane wave. So in my opinion, and I've written a couple of papers on this for electromagnetics, but and I'm happy to discuss more. But the point is that probably for this specific medium or arrangement of particles, the assumptions on the model are too simplistic. And I totally agree with your conclusions, by the way, that essentially, I mean, you made this beautiful progress in proposing this non-locality model, but of course, it cannot apply to all possible combinations, and it may be possible that we need additional non-locality terms to get a better homogenization. But for sure, for certain range of frequencies in the long wavelength limit, this makes a better description than neglecting the non-locality at all.
Yes, I tried to sort of cover myself to some extent by showing those funny pictures of in one dimension, just to point out that actually when I thought of this, although I regard whatever I do as honest because I've said exactly what I've done and then I followed it through and done it. And whatever I've written up follows from a definition, an explicit definition. And that's all I'm claiming. But I figured that it was more likely to be of use at at long wavelengths, long effective wavelengths, than anywhere else. And that was why I went into that. I do believe that if you want an honest, more accurate description of the random medium, you need to know something more than just the two-point correlation function. If you only know the two-point correlation function, what are you going to do? Just guess something and you don't even know what it is, or use what you've got? And if you're using what you've got, well, I've been unable to think of anything better than looking for a stationary point of a very well-established variational formulation. And that's really all I can say about it. Namely that I don't think I've ever gone around making huge claims for anything I've done. And I do actually think that my equation, my formulae, even the ones that look like they're going in a peculiar direction, do still confirm that the total energy is dissipated. And also nothing happens, cause comes before effect. They are causal. And that's as much as I can say.
Yeah, I mean, the point I'm making is that, so first of all, I totally agree that applying that formulation, you would get those results. This happens also in electromagnetics. And my point is that this implies that not necessarily this model can apply to the specific sample we're analyzing. And the reason why that cannot be acceptable, let's say, if you have that wrong turn in this anomalous dispersion in the frequency response and this effective gain in one of the elements, is that if that description would be valid, then by taking a very thin sample of that material and putting it in a structure that enhances one of the two components of the field, let's say the pressure, for instance, if the density has the wrong turn, you would expect to get gain out of that system, right? Even if for a plane wave.
I don't know that I'd expect to get gain, because the stress is not only coupled to the strain, it's also coupled to the momentum. So I don't think I'm saying that the strain, excuse me, I don't think I'm saying that the stress itself is not decaying. I'm only saying that the thing that I call C effective looks that way. It doesn't mean necessarily that the mean stress goes that way. And I think if you're doing experiments, you'll observe the mean stress if you're lucky. You can certainly observe the mean strain. And
absolutely.
You can even do it point-wise, I guess. But that might be the thing, that with that S in it, there's not a contradiction. But I don't want to argue too much about it. I only say...
Yeah, anyway, we can discuss it more.
...makes in the sums.
But thank you for the beautiful talk and great insights.
Nice to talk to you anyway.
Yes.
Thanks a lot, Andrea. These are really wonderful questions to ask. And please, I would like someone else now to come forward with a question, another question. I've got many as well, but I'd prefer that someone else asks questions. So I've got a naive questions. Is there some kind of alternative theory for water waves? When you have a liquid phase, can you also have your kinds of equations? So you have a solid and a liquid phase mixed together.
I'm thinking, I guess I need to ask some questions. Is this still linear? There's no large displacement or anything?
In a linear approximation, everything is linearized.
Yes. I believe so. I can only say I believe because I've not done it. And I wouldn't like to say how useful. I don't know. The thing is, if I was doing water waves, well, what would I be considering? Would this be a suspension that you're talking about?
Yeah, this kind of random suspensions, you know, in water waves. So colloidal suspensions at the surface, free surface of water. So you have...
Okay, yeah. Well, that's a class of problems that I've never looked at all. So it's hard for me to say, but I do actually believe that the variational principle, or some version of that variational principle, could be applicable to describe that problem. How useful it would be, I can't possibly say. But I do believe it would work. If I just took two elastic media and the displacements are all small, all I need to do is to make the shear modulus of one of the media 0, and it seems to me I'm there with you. Although then there's a slight... Then the next question is, does the fluid have viscosity, or does it... If it's an inviscid fluid, you know, you lose some of the stress components, you change the boundary conditions. I would guess that it could be done, but well, I wouldn't like to try to do it If you could see my blackboard behind me, I wouldn't like to try and do it on my blackboard now, in case because of the high probability that I would fail first time.
And also, there is another obvious question. There is a nice link with time-modulated media. So now when people look at elastic or acoustic media and they start vibrating them, then they end up with your equations, actually. Can you comment on that?
No, I can't, because I've never looked at it. That's a very interesting statement that you've made. Very interesting indeed. One reason why whatever I've said today would be a disaster in that situation is that I've Laplace transformed. And my variational principle from which I started was one in which time only appeared through a convolution. And so the variational principle I was using isn't really a good physical principle, it's a mathematical one. It's fine if you've got S in it. If you're in the time domain, my products become convolutions. And that kind of principle was first proposed for elastodynamics by Gertin in about, I don't know when, 1964 or something. But as soon as the medium properties are varying in time, of course, I shouldn't do that. It may be that I could start with Hamilton's principle or something or other, I don't know. But it would be a long way off what I've spoken about today, that's all. So I'm very interested to know that the similar forms kind of come up. And I guess the way they come up is surely a little bit different from this way.
Yeah, we'll send you a paper by the team of Hussein Nassar, and they actually, by time modulating the medium, end up with the exact same equation as yours.
I'd be very interested to see it.
Yes, sure.
Yeah, you know I'm a poor old man and I'm retired and I only work part-time, if that, and so I'm not keeping up to date too well.
But so what I try to imply here is that it's very interesting to see that your equations seem to arise in various subjects, and even loosely related subjects, people get your equations. So it's
very entertaining. Good, yes. Thanks for the comment.
Okay, so I think André Diatta has a question for you. André, can you come forward?
Yeah, hello. Thank you, Professor Willis, for this wonderful talk. I just have one question. Would there be any possibility that the theory has a zero frequency counterpart in mechanics, elastostatic?
Elastostatics doesn't have to be zero frequency. What it has to be is zero density. And if the frequency is low enough that the density doesn't matter, then you've got there. I mean, in a sense, I started doing elastostatics before I ever started doing any of this, and it's correspondingly simpler. And I mean, if you've got no dynamics, you're not going to have coupling between stress and velocity. So, you know, that's one of the things that's kind of amusing to me. It's one of the things that's amusing about doing the dynamics. So sure, yes, indeed, the entire machinery goes through, and it's actually much simpler in statics than it is in dynamics. But what comes out that may be interesting, I wouldn't like to say, I don't know.
And as an aside question, can you comment on your paper with Graham Mitton and Mark Brian? So you made some geometric transforms in the Navier equations, and then you end up with your equations, actually.
Yes, yes. Well, that's, you know, it was Graham that got me back into this because he knew that I'd done things that could be relevant, you know. And if you want to go in for transformation acoustics or whatever you'd like to call it, unfortunately, as you know, with the elastodynamic equations, you do get this funny term coming in. And the way that well, there were two things. One is that more enhanced system is closed under transformations, under general transformations. That's good. But the other thing is, if you wanted to build a material that would realize your transformation elastodynamics, at least I was thinking at the time that the way to do this would be to make a virtue of what otherwise could be a nuisance, that you were going to get these coupling terms. And but then the question is, could you ever design a composite which would do it? And I don't know the answer to that. Yeah.
Perhaps Martin Wegner could comment on that. You would be able to make a comment, Martin?
No, actually, I'm not able to make a comment. Sorry.
I was trying to test my luck. Okay, thanks anyway. So any more questions on, any subject related to Willis equations or this seminal work? I mean, I've got many questions, but really it would be much better if someone in the audience would come forward, and especially young researchers. It's a unique opportunity to talk to Professor Willis, I can see many young people in the list, so don't be shy.
Well, don't press them too hard. You might end up getting one of them to ask me an extremely difficult question.
Okay. Okay, so with that, I would like to... Yes, please.
So I see that there's no brave young researcher, so I'll maybe make a question or a comment to John, if I may.
Hi, Gal. I can see your name. I don't see a picture, but never mind.
Well, you're not missing too much. I didn't get any better looking than the last time that I saw you, but here's the video. So I have one comment and one thing or two things that I would like to hear your opinion about them. So I'll start with the comment, which is shorter. I actually, together with my postdoc René Pernas, we did a generalization of what you did by starting with a piezoelectric material. So what we get by accounting for the electric displacement field and the electric field, we get in some sense a generalization of your cross-coupling terms, right? Which couple the momentum and the electric field and couple the velocity with the electric displacement field, which is kind of nice, I think.
Yes.
And in some ways, it falls also into the realm of B anisotropy in electromagnetics, and it gives a nice, unification of the electric problem and the mechanical problem. This is just one comment that follows Sebastian's comment about what follows from your work. And the second thing that I wanted to ask you is about your perception about the eigenfields, right? So you've pointed out that owing to the fact that the operator is non-local, then the effective relations are not unique. And in fact, without those eigenfields, you don't need those cross-coupling terms, right? Because the independent fields are related, and actually Nassar did a nice work on that, and it shows that in some way you can absorb, right, the cross-coupling terms into the direct ones, right, into the, let's say, the stiffness operator and the mass density operator, right?
You can for acoustics, you can for a 1D problem. I don't know if you can for a really general problem. If you say you can, I accept what you say, but I'm not sure. I somehow doubt it. Let's put it that way.
Okay,
because
so,
of, for instance, of Norris.
Excuse me?
because of work, for instance, of Andy Norris, who's studied problems of stratified media with a completely different machinery than mine. And he felt that these coupling terms were unavoidable. He's written that.
Okay, so
But I agree they can be got rid of in simple problems, that's for sure.
So I think otherwise. I think that these cross-coupling terms can always be absorbed into the direct couplings, I would say. And this is why we need your, let's say, introduction of the eigenfields, right? The eigenstrain, if you will. Because without those, the independent fields are always related one to another.
Well, if that's what you say, that's fine. And if what you say is correct, you've just demolished the whole of this coupling theory. And
well, that's
whether you're right.
Well, that's not exact because, like you said, once you introduce those eigenfields, you can make the set unique. But
you don't need it.
This brings me.
If you're going to have eigenfields, you don't need it.
Okay, this brings me. Okay, so this brings me to a discussion that I had with Milton, right?
Yeah.
So Milton pointed out that those, in a sense, cross couplings are, let's say, most evident or most necessarily in the local limit. There you cannot avoid their necessity, right? Because you can only manipulate the independent variables are dependent only in the non-local region, right? Because there the averaging operator and the derivative operator commutes, right?
You can't avoid them at low frequencies or something, which is what I think you're saying. That means you can't avoid them. I mean, you can't say you can avoid them and then tell me immediately, well, in the local limit, you can't avoid them. That's inconsistency, I think, anyway.
Okay.
I tell you what, we can think about it, not now on the screen. If I think of anything, I'll send you an email.
Excellent. So thank you for the talk, and I'll turn off the video now.
Okay, nice to see you.
It was great to have you with us, Gal. I remember vividly when we met in Israel.
Back in the days when there was no COVID.
Yeah. So I guess, Professor Willis, you were thinking of the work of Andrew Norris. He has this kind of propagator and he has a stratified medium. And when he is doing some kind of effective medium, he gets your coupling term.
Yeah, that's what I was thinking of, yes.
Yeah, it's the Proceedings of Royal Society paper. Yeah. I can see it. Okay.
A few years ago.
Yeah, a few years ago. Okay. Shall we close this discussion session, and we should thank our speaker again for this wonderful talk and for giving us the opportunity to discover this great set of equations that I think are still really promising, and I think we shall use in the years to come. So thank you very much, Professor Willis, and well.
Thank you.
And next week we shall have Anne-Sophie Bonabendia, who will give a talk about corner waves. Well, actually, she calls these waves black hole waves, propagating at the intersection between media with sign shifting parameters. So it's another interesting subject, I believe. Okay, thank you so much, everyone, and I hope that you have a wonderful evening or morning if you are in USA. Bye-bye. Bye, Vida.